All right, thank you everyone. We're in our last session of the day. We're going to start with Jason Wang, who's going to tell us about the Roman chronograph instrument. So here you go. This is an invited talk, and you just advance with the bottom one, and there's a laser there. Yeah, nice. You can see your time right there.
Okay, sounds good. Okay, hi everyone. We're going to take a little break from our regularly scheduled wide field imaging to talk about this other instrument on the chronograph, the O in the Roman Space Telescope logo, which is the chronograph instrument. And I'm presenting this on behalf of our Roman chronograph team. And I guess before we get started on that, I just want to say, it's really appropriate that we're flying a second chronograph instrument on the Nancy Grace Roman Space Telescope. Nancy Grace Roman was NASA's first chief astronomer, and she actually wrote an article in the Astronomical Journal that says, as seen from the distance of Alpha Centauri, Jupiter, at its maximum apparent separation from the Sun, 3.94 arcseconds, will be a star of 23rd and a half magnitude, and that a similar planetary system around Alpha Centauri would be within the reach of our largest telescopes if our terrestrial atmosphere did not limit our resolution. So I think this is really fitting that on the Nancy Grace Roman Space Telescope, we will be trying for the first time to image another exoplanet in reflected starlight, just as Nancy Grace Roman herself had predicted. All right. Yes. So imaging exoplanets is not easy. Here's a simulation of just a star in a planet system. So here you can see the star, and this is a simulation assuming a perfect telescope with no aberrations. So this is a circular telescope. There's not a weird pupil like in the Roman Space Telescope, but there's no wavefront errors either. We have completely perfect optics down to the nanometer, down to the picometer level. And you can see that although you can see the planet, you can see the star, you can't really see the planet. The planet is hidden underneath the diffraction of starlight. That the fundamental diffractive nature, the quantum nature of light, prevents us from seeing the planet because it's hidden underneath the glare of the star just due to the finite size of our aperture. So in exoplanet imaging, we have to invent special optics. We call them chronographs. And these chronographs, what they do is suppress starlight at particular separations from the star, the ones that we're interested in, to basically prevent that diffracted starlight from landing at particular locations on our detector so that we can see these faint planets that are orbiting their stars. In this simulation here, we're talking about a planet that's about 1 million times fainter than a star. You'll see we'll be talking about contrast, which kind of is a flux ratio between a planet and its host star. This is a contrast of 10 to the minus 6. And this is kind of what we're doing nowadays with current observatories. But we need to go beyond this with Roman, and just a chronograph alone won't get us there. We talk shortly about why. So this is kind of tells us the landscape of exoplanet imaging. It's a bit of a technical plot, but if you bear with me, I promise you that it's interesting. So on the y-axis, this is the flux ratio between the planet and its host star. So like in the last simulation you just saw, that planet was about 1 million times fainter than its host star, 10 to the minus 6. On the x-axis is angular separation, the distance of that planet from the star in arcseconds. Right now, with our current generation of telescopes, this is the ground-based AO imaging and also JWST in space. We're imaging planets that are about 10 to the 6 times fainter than its host star, 10 to the minus 6, at angular separation about 0.5 to 1 arcseconds. That's kind of our current state of the art. In the future, we have this idea to be able to image an Earth-like planet around another Sun-like star. That's down here. That's the concept for Habitable Worlds Observatory. It requires us to image a planet that's 10 billion times fainter than its host star, 10 to the minus 10, at an angular separation of about 0.1 arcseconds. So we're about 4 orders of magnitude away from that with our current technology that we've demonstrated on sky in space. What the Roman chronograph will do at this technology demonstration instrument is basically try to bridge that gap by basically 3 orders of magnitude, down to about 10 to the minus 8 or 10 to the minus 9 levels in our optimistic case. Our technology requirement level is 10 to the minus 7, but we hope to do better than that, obviously. to put us within striking distance of this 10 to the minus 10 contrast that we'll need for a future observatory like habitable worlds. And I'll say that the performance, the reason why we're hitting 10 to the minus 9 is limited by the kind of the inherent telescope architecture of the Roman Space Telescope. But even despite that, we're able to get down to potentially very interesting science if we can achieve kind of our goal performance levels that we're aiming to with the coronagraph. So if you don't pay attention to the rest of the talk, this is the summary slide of the Roman chronograph. This is my little cartoon. So our Roman chronograph is kind of a series of technology demonstration hardware that we're flying. Our goal is to basically image, hopefully, planets that reflect the light for the first time. But we're primarily a technology demonstration instrument. But obviously, we can demonstrate our technology on scientifically interesting targets whenever possible. One of the things you'll hear about shortly is we're going to be doing this thing called dark hole digging to carve out an area around the star that's almost devoid of starlight, and so that we can see these planets. And we'll be operating, unlike the WFI, actually at visible light wavelengths between 500 and 900 nanometers. So we're actually at a completely different wavelength range than the rest of y'all. We have about 3 months, 90 days of observing time in the first 18 months of Roman, and we've planned the first 6 months already, and I'll talk about what kind of plans we're going to go with in the very beginning of our first 6 months of operations in our observation phase. So some of the key technologies that we're going to demonstrate on the Roman chronograph for the first time in space on real targets. Like I said, this key thing is this idea called dark hole digging, and dark hole digging is basically trying to optically cancel out starlight in a particular region around the star, so that part of the region of the star is devoid of starlight, so we can see faint sources like exoplanets orbiting the star. We're going to do that with these deformable mirrors, 48 by 48 large deformable mirrors that have a stroke resolution down to about 10 picometers. This is a fraction of a hydrogen atom that we're trying to control our optical wavefront down to that level of precision. In addition to doing this dark hole digging process, we'll also be flying these very low noise EMCCDs that hopefully will allow us to achieve photon counting flux levels. This is extremely important for the next generation of exo-Earth imaging, because an Earth-like planet around another sun-like star might be faint as maybe 30th magnitude in the visible, and we want to take a spectrum of it to look for molecules in its atmosphere. So basically, every photon from these sources matters, and we're to be flying some new technology to see how viable it is to kind of be able to identify and count every photon that arrives from these astrophysical sources that we want to detect. We'll also be flying these next generation coronagraph masks. You can see these cool designs here. These kind of cool ripples and things like that, they actually do things, and they're able to allow us to suppress diffraction down to the levels that we need. And in addition, we'll also be doing data analysis in a completely new contrast regime where we're dominated by different kinds of optical aberrations that behave differently than what we're used to in the field of exoplanet imaging. So we'll have to figure out how to do that as well. So here's a picture of the chronograph instruments. This was assembled at JPL. You can see actually the light path. The light from the telescope comes here and basically bounces off a bunch of different mirrors. It goes through our two deformable mirrors that basically are able to manipulate the optical wavefront in order to dig that dark hole that I was talking about. It goes through a series of coronagraph optics that basically suppress the glare of the star further. And then we also go through some color filters. I really like these filters. This is a nice picture of them. Because we're in the visible, these are actual, true color photos that we can take of our filters. So we have filters in the pink and the green and the purple and etc. Before landing onto our EMCCD photon counting camera. This is a picture of the chronograph fully assembled at JPL going into the vacuum testbed chamber. This is where we are able to kind of simulate the vacuum conditions of space and test all these optics as they're designed to operate in the vacuum of space. These were the results of that test. So what you're seeing here, this is what's called a contrast curve. So we're plotting how much starlight have we suppressed So this is 10 to the minus 6 for reference, that where we're currently at. That's right here, and we're trying to go deeper than that. So this is real data from the chronograph taken in the JPL vacuum testbed chamber, the TVAC data, and this should be an animation that plays. And you can see as we go through iterations, we're optically canceling out more and more of that starlight, killing all of this, causing the starlight to interfere with itself and cancel itself out to create this very dark hole that we'll be using to search for exoplanets around. So this is what we were able to achieve in the lab in kind of space-like conditions of 10 to the minus 8. So we're hoping that we can do similar, if not better than this, when we also launch and go on Sky as well. Since the assembly at JPL, the team that has been working on the chronograph has really grown. We've launched this community participation program that is basically a bunch of scientists and engineers are getting together to basically do everything for a chronograph. This includes, helping with commissioning of the telescope. It includes calibration, writing the data reduction pipeline, planning all our observations, figuring out what the most interesting science we can do with our current understanding of our performance is. The community participation program consists of 11 US-based and funded teams. The Roman project team members, say from JPL and IPAC. Also international partner teams that have made contributions to the chronograph itself, from the European Space Agency, the Japanese Space Agency JAXA, the French Space Agency CNS, and also MPIA as well. And we also have interested community members that have joined our team. We're led by Vanessa Bailey here from JPL, who's one of our CPB co-leads right here, and also a rotating co-lead, currently Skylar Wolf at University of Arizona, are our two co-leads of the community participation program. We, on the chronograph, have three main observing modes. One is kind of our nominal required observing mode. This is our narrow band, visible light, 575 nanometer imaging mode, where we're going to dig a dark hole and try to image planets potentially in reflected starlight for the first time. We also, in addition to that, have a second wider field of imaging mode. This is different from the WFI wide field. When we mean wide field, we mean we go out to 1.4 arc seconds. Sorry, this is wide for exoplanet imaging people. I understand that this is the narrowest of narrow fields for everyone else. So we have these two modes. We can operate in band 1 at 575 nanometers and also at band 4 and 825 nanometers. We also have the ability to put it in a prism. And that prism will spectrally disperse the light, enabling us to, if we detect a planet, potentially also spectrally disperse that light through a slit spectrograph post-coronagraph, and try to look for absorption lines in these planets' atmospheres, such as sodium and potassium. These are refractory elements, true metals that we often have a difficult time measuring in the near infrared. So going to the visible light wavelengths and measuring these refractory elements can tell us about planets' compositions and how they formed. Our main requirement is our technology demonstration requirement of reaching better than 10 to the minus 7 contrast on a V of 5 star in band 1 at 6 to the 9 lambda over D. But obviously, if you give a community an instrument like this, this is not the only thing everyone wants to do. We solicited community input on what to use the Roman chronograph to observe in. So in January 2025, we asked the community, just take 1 minute and tell us which of these science cases is the most interesting to you. And give it a low priority, medium priority, and high priority. And you can see the highest two priority science cases is imaging of a giant planet in reflected starlight and spectroscopy of a reflected light giant planet. Those are kind of the most novel things that the Roman chronograph has the potential to do, and will kind of set the stage for a future mission like Habitable Worlds. In addition to this this community interest survey that took very little time for anyone to do, so we got a lot of input on this. We also had a white paper call in the summer of 2025. We had received 80 white papers spanning various science and technology demonstrations. They gave us a bunch of great suggestions, such as target selections, which planets were disk-bearing stars should we observe, even giving us ideas for possible AGN or transient science cases that we should be aware of. These are oftentimes probably too faint for what we are going to plan to do in the first 6 months, but maybe possible in an extended mission. gives us ideas for how do we validate technology that's important for habitable worlds, and also algorithms that we could try to deploy on the Roman chronograph that will also teach us about what are the best wavefront control algorithms to reach the 1 picometer kind of optical stability that's going to be needed for the habitable worlds observatory, and we want to be able to test out some of these ideas on sky. All of our white papers are published to Zenodo, so if you're interested, you can go to this link and read all the 80 white papers that were submitted. Using kind of the community input of what, in general, based on vibes, the community wants to see, as well as the specific recommendations and detailed suggestions given to us in the white paper call, we designed the first 6 months of the Roman chronograph observation phase, and it can be broken up roughly into 3 categories. The first category is to try to image the first images of planets in reflected light for the first time and be able to study the albedos of typical Jupiter-like planets. We're gonna, in the first couple months of the Roman observation phase, try to observe 3 of our hardest targets, UPS AND, EPS Ari B, and 14 Her B, and try to detect these planets in reflected starlight. The reason why we're doing it in the first month is due to timing constraints, and I'll talk about that in just a second. In addition to this, we'll also be doing imaging and spectroscopy of self-luminous planets and brown dwarf companions. There's a whole slew here for those aficionados in the room. And in addition to that, we'll also be trying to take images and do polarimetric imaging of both debris disks and also warmer dust, all the way down to potentially trying to image exozodiacal dust around other stars, which is both interesting from this is a set of dust near in the terrestrial planet-forming zone that we haven't really imaged and reflected light before, but also this will tell us about the difficulties of imaging exo-Earths for habitable worlds as well. So we have, for the aficionados in the room, selected targets for all of these various science cases for our first 6 months of observations. Our typical observing sequences look something like this. First, we go to a bright reference star and do this thing called dark hole digging, where we dig and try to kill as many of these speckles as possible to give us a dark hole for which we search around for planets. And then we slew to our science target, observe the science target, and we're going to roll the telescope around to kind of differentiate between astrophysical sources and speckles, and then go back to our reference star to get additional reference star images to kind of model the changing speckle field, as well as every about 20 hours of observations, re-dig our dark hole again, because our dark hole will degrade over time. Our observations can take tens of hours, indeed, we can also, during those tens of hours of chronograph observations, we can have simultaneous WFI long stares at whatever patch of sky WFI is pointed at while the chronograph is taking data. I don't think very much about the WFI. For me, it's our guider camera, but I guess for you all, you might be interested in the simultaneous data that comes down while we're doing our chronographic observations. This part, the bright reference star that we're going to first dig a dark hole, turns out to be actually one of the challenges of the Roman chronograph and possibly one of the challenges for habitable worlds as well. This reference star has a lot of restrictions. The reference star needs to be bright. This is because to optically kill speckles, kill these diffraction artifacts from the star, you have to be able to see them. And these speckles are just as faint as these reflected light planets that we're trying to see. So these are 20, 22nd, 25th mag speckles that we're trying to kill. So you need, the brighter the star, the easier it is to get the right amount of signals and noise and the short enough exposure time to actually see and optically cancel out these speckles. So to prevent prohibitively long exposure times for dark hole digging, we set a requirement that the stars, reference star, need to be brighter than V of 3 in our visible light wavelengths and I of less than 1.25 in our longer near-infrared wavelengths. It also turns out our chronograph works so precisely that even a partially resolved star will mess up our dark hole. So we have a restriction that the star's angular diameter needs to be less than 2 milliarc seconds. And we also need to make sure the star has no binary companions that can mess up as well with diffracted starlight. And the star has to be within 5 degrees from the science target in terms of observatory pitch, the amount of sunlight being coming onto the observatory. With all these restrictions of extremely bright star with almost no a minuscule angular diameter, this basically restricts us to kind of high mass stars. O and B stars are kind of far enough away that they have they have less than 2 million arcseconds angular diameter, but still, thanks to the mass luminosity relationship, are still bright enough that they're V of less than 3. And we know about the high binarity fraction of high mass stars. So we have basically undergone a big observational campaign of spending hundreds of hours of telescope time to basically vet all of our O and B star candidates to see which ones may not have binaries. And we're talking about not just like equal mass binaries, we're talking about extreme mass ratio binaries that basically until now haven't really been probed. Like how many O and B stars have M dwarf binaries close by? So I think that's a question we don't know. So we've been trying our best to vet these stars with the instruments we have. Obviously, they're not as sensitive as the Roman chronograph, so we can only vet so much of parameter space. Here's just an example of a binary with a delta magnitude of 12. So this is 10 to the 5 times fainter than the star itself, and that binary will completely mess up our dark hole. Similarly, if we had a really wide separation binary, even with a delta mag of 2.5, 10 times fainter, at about 10 arc seconds, the diffractive glare of the star, the wings of the PSF will basically as well also mess up our dark hole. So we have extremely stringent requirements on the lack of binaries for these high mass stars that we're using as our reference stars. And this has caused us some considerable pain, but I think we found a few that are good enough. And this is a work led by Justin Hom at University of Arizona, spanning, like I said, hundreds of telescope hours over the last 2 years. And we've been able to end up with about 20 to 40 stars that are kind of good enough that we think don't have, to our best of knowledge, don't have any binary companions. And here's a map of the sky, and plotted in the color bars is observational efficiency. It's a measure of what percentage of the time that a star is visible to Roman is there also a suitable reference star within 5 degrees of delta pitch that could be observed at the same time. And you can see that we've done enough vetting that basically, at least for our band 1 narrow field, our most required mode, almost all of our targets have at least about 80% efficiency or better. So this is a breath of relief, but something we were really worried about in the last 2 years as we were preparing for the chronograph mission. This is not our only scheduling constraint, though. These reflective light planets are really finicky. You should go check out Clarissa's poster here about trying to schedule these reflected light observations. But it turns out that basically we have very narrow timing constraints. This is one of our first planets, UPS and D. And the reason why I say we're observing it in the first kind of month or two of the Roman chronograph observation phase is because there's a good chance for us to detect it now. If we don't observe it now, this year, we're going to have to wait a whole year before the next observation becomes feasible. And this is actually this is our best one. For some of our other targets, if we don't observe it in December or January of this year, we'll have to wait 3 years or more to observe it again. So I encourage you to check out Clarissa's poster if you want to learn more about this, but this is a combination of having to figure out where the planet is in its orbit and observing it at particular parts of its orbit where it's reflecting the most light. We think about like the phases of the moon, and the fact that we need to observe we have to observe planets when they have the best phase coming towards us, in addition to being far enough away from the star that they can be spatially resolved by the Roman instruments, the Roman telescope as well. So you can think, oh yeah, reflected light planets, these are really hard. Why don't you start with something easier? Like there's like known exoplanets that have been directly imaged. Why don't you observe those instead? So we've also looked into that. So this is the HR 8799 system, very famous directly imaged system. We've considered trying to observe spectroscopically one of these planets by putting the slit and dispersing the light of the star. These planets are exceedingly easy now with modern kind of ground-based observatories. It takes us a single minute on on something like the Gemini planet imager to detect one of these planets. But turns out when you're going to the visible light wavelengths in the wing tail of the blackbody distribution, and also due to these metal alkali absorption lines, these planets can be extremely faint, and the model uncertainties are very large, with more than an order of magnitude in uncertainty in these models. And so some of these observations can take tens, if not 50 hours for us to even detect some of these planets with the Roman coronagraph. So it's not just like the reflected light planets are hard, the self-luminous planets are hard as well, just because of how faint they are at optical wavelengths, even though they are bright and visible in the infrared. I'm going to skip this. This is our data reduction pipeline. We spent a lot of time writing our own data reduction pipeline. I hope it works. I'm leading the data reduction pipeline, so that's why. After our first 6 months, we're hoping to really push our faint star performance, going from V of less than 5 to V of less than 9, to try to open up a bunch of new science cases, including protoplanet and protoplanetary disk systems. We're hoping to commission additional modes, improve observing efficiency, and we're also going to probably be soliciting new community ideas again in summer of 2027, given the published on-sky performance of the instrument, asking again the community, what should we do now that we kind of know what the coronagraph is capable of? So I guess I'll end it here, and I'll be happy to take any questions. Thanks.
Thank you so much for that great overview. Okay, questions for Jason? I have one that I can kick off of. Oh yeah, you go first.
Hi, great talk. I was just thinking, what will be the value of the voltage that will be applied to the actuators behind the deformable mirrors?
What are the actual voltages that are going to be applied?
Yeah, in the actuators.
I can't say I know the exact voltages that will be applied off the top of my head.
It's
Bertrand.
100 volts is what
up to 100.
Up to 100 volts is what's being said.
Can I ask a question? I'm just stepping as the chair.
Sure.
Can you comment a little bit more on the science, the new science that we'll learn from observing these planets in reflected light? Like, what new things will we actually learn from this, as opposed to self-luminous?
Yeah, so the question is, what will we learn from reflected light planets? We haven't really ever, we have very few planets that have any reflected light signal. So understanding about the atmospheric composition of these planets will tell us a lot about things like clouds and hazes. These are things that we don't understand on Earth really well, let alone other exoplanets. And if you're going to try to do a mission like Habitable Worlds and image a bunch of planets in reflected light, we have to start somewhere, and this will kind of give us the first glimpse of what is the diversity of planet brightnesses and albedos at reflected light wavelengths. Well, there's been some work on this, done this with tests, but we doing this with more temperate planets with different kinds of photochemistry. This will be really interesting, I think.
Thanks. Oh yeah, Jessica?
I had a question about what, if anything, is going to be done to prepare for possible fainter targets in the post 6-month time period. How well can you preserve the dark hole for targets that are fainter, where maybe the contrast requirements are not so stringent, i.e. not exoplanet hosts, but AGN host galaxies, type things like that?
Yeah, I think a lot of this is kind of operational. It's just like given the amount of resources we have to kind of develop, make sure our star acquisition algorithms work. We've designed it for the really bright case where we can tune all these knobs. And basically, what we'll have to do, what we're planning on doing, in fact, in the first 6 months, is trying to turn off some of these knobs and seeing how well can we acquire stars, put them behind the coronagraph, keep them stable without some of the loops running that require extremely bright stars running at really high frequencies.
We have a question up there. Seppo up there. Thank you.
Great talk. I was just curious, for like the WFI, we use the up the ramp to do jump detection for cosmic rays. What method are you using for the CGI to detect its cosmic rays?
Yeah, so we don't have an infrared detector, so we have a we are basically using the brightness, the counts, as well as the shape to detect for cosmic rays, just like as you would kind of with a normal CCD.
Okay. Any last questions? Oh, we have Ryan.
Thanks, Jason. What are the plans for the CGI, like in the extended mission? Is it going to be part of the overall like call for proposals, like as an offered instrument mode?
As far as I'm aware, we're not offering CGI in the call for proposals. It's going to always, I think, for at least in the near future, always be gone. All the time allocation will be done through the CPP team, just because it requires very specialized infrastructure and technical knowledge to even schedule these observations.
Okay, even in the extended mission, there might not be.
I can't comment on an extended mission.
Julie says yes, even in an extended mission. All right, let's thank Jason again. Thank you so much.